Welcome to today's deep dive. We're on a mission today to decode a really fascinating presentation, specifically document EP0075.
Right, which takes us straight onto the R&D and manufacturing floor.
Yeah, exactly. Because, when you look at a flawlessly running machine, whether it's a massive jet engine or a precision robotic arm, you just see smooth motion. But behind that quiet motion is this operational language built on extreme violence and microscopic precision.
It's entirely an illusion of calm.
Hmm.
I mean, to build machines that survive immense physical forces without tearing themselves apart, engineers rely on a very specific set of terms.
Right.
We're looking at 5 key concepts today, and they aren't just dry vocabulary. They reveal exactly how we manipulate physics into submission.
And that manipulation starts with carving out the raw metal, right? The presentation highlights power skeeving as this ultimate efficient machining solution.
Yes, particularly for cutting internal ring gears with a .5 module, which basically means gears with incredibly tight, fine teeth.
Okay, so historically, cutting those internal teeth was a pretty slow process.
Oh, very slow. You had a technique called hobbing for continuous spinning cuts, and then shaping for a pounding up and down stroke.
Ah, okay, so power skeeving is revolutionary because it merges the two.
Exactly. It's one high-speed, continuous process.
So instead of swapping tools, it's almost like, I don't know, using a spork. Like combining two tools into one highly efficient motion to just get the job done faster.
Yes. A spork is actually a great analogy. You get the continuous rotation of hobbing combined with the vertical carving action of shaping. It cuts those teeth in a fraction of the time.
Wow. But, I mean, a newly carved part like a central sun gear isn't ready for an engine's torque right off the bat, is it?
Definitely not.
Right.
Raw steel straight off the cutter would just shred itself. It needs case hardening.
Which the document mentions requires a surface hardness of HRC 58 to 62, right?
Right. By using heat treatments like carburizing, engineers basically bake carbon into the very surface. It creates a highly wear-resistant shield, but crucially, it leaves the inner core tough and flexible.
Oh, so they are turning gears into M&Ms.
I'm sorry, M&Ms.
Yeah, you have this hard, protective outer candy shell taking the friction, but a softer, shock-absorbing chocolate center. So the whole gear doesn't just shatter under impact.
That is actually a brilliant way to picture it. The armor is essential. But even with that hardened shell, microscopic imperfections can still cause massive failures.
Which is where lapping comes in.
Yes. Lapping uses fine abrasives to achieve incredible surface finishes. For intricate parts like cycloidal pins and discs, this microcutting kills friction and deadly thermal expansion.
Okay, wait, I'm stuck on something here. If we just turn this gear into a bulletproof M&M, why are we suddenly worried about a microscopic scratch?
Because friction creates heat, and heat destroys precision. If a microscopic bump causes friction, the metal physically swells, and the machine jams.
Oh, wow, I didn't even think about it swelling.
Yeah, but heat isn't the only enemy. Real-world torque literally bends the metal. That's why engineers use profile modification.
Wait, meaning they intentionally alter the theoretically perfect shape of the gear teeth?
Yes. Under heavy load, the steel shafts holding the gears will deflect. If you rely on a mathematically perfect gear shape, that shaft deflection pushes all the heavy force to the very edge of the teeth.
And that edge loading causes terrible noise and rapid wear, I imagine?
Exactly. So, engineers intentionally shave microscopic amounts off specific parts of the teeth to compensate. They anticipate the bend so that when the shaft inevitably flexes, the gear teeth align perfectly in practice.
They build it flawed so it works perfectly under stress. That is brilliant. So we've carved it, armored it, polished it with a slurry, and modified its shape. How do they actually prove all these pieces play nice together?
By measuring the total runout, this is the ultimate metric for geometric precision. You measure the total surface area during a rotation.
So it's basically checking if the whole assembly is perfectly concentric.
Yes.
Ah.
Controlling total runout is the only way to guarantee uniform load sharing across a planetary gear system.
Right, because if one gear wobbles even a fraction of a millimeter, it hogs the mechanical stress.
And that uneven distribution will tear the transmission apart in no time.
Wow. So it all really comes down to the journey of the gear, from an incredibly efficient cut to a hardened shell, physically modified for stress, and perfectly balanced.
It proves engineering isn't just about perfect math on a whiteboard. It's about anticipating the chaos of the real world.
Absolutely. Which leaves you with a final thought for today. Profile modification teaches us that a theoretically perfect shape will fail under real-world pressure.
Right.
So what other perfect systems or plans in your own life are failing right now simply because they haven't been intentionally modified?